True. Hadn't really thought about that until just now. Yeah, I figured. It's been a popular name back, however. When were you born? What I want to do today is let's read through this dumb tic-tac-toe and talk about let's sketch sort of how the program's going to look, and then I'm going to go back and sort of by way of introducing processing, we'll try to implement a lot of this stuff. The thing that I'll stop at is the actual move analysis for the AI, such as it is. So the program should be smart enough to take advantage of two of its own marks in a row and to block two of its opponent's marks in a row. If neither is possible, you can have it make any legal move. The program should start by asking whether the human or computer will go first. The first player's moves are always represented by X and the second by O. So whoever decides to go first, regardless of who goes first, that player will play with X's. Okay, so let's talk about what's going to happen in this program. Just big pictures kinds of things. What are some of the big tasks that have to occur in order to make this thing run? First step is probably who goes first? Yeah, AI or player. So how do you see this going? Who goes first? Do you have an idea of how you might make that happen? I know that you don't know the full feature set of processing, but just pretend you didn't know anything about processing. You're just designing a game. How would you figure out who goes first? Create a couple of buttons, okay? Pop a screen up there with two buttons. And do you want to go first? Yes or no? Do you want the computer to go first? Right. It's just one question. Would you like the computer to go first? Yes or no? So this would be a simple two-button screen with a prompt. Who goes first? And then something like that. If you click computer, then what's going to happen? So the board will appear, right? And there'll be an X somewhere on it. If you click human, what'll happen? The board will appear and wait for the human to select a move, right? Okay, so that's step one. Let's get into the nuts and bolts of playing. I guess we should also, how do you want to keep track of this decision? This decision is obviously important to the remainder of the program, right? How do you keep track of that in the program? Some kind of Boolean. First player human, maybe you could call it. First player human. If it's true, then the first player was human, and if it's false, then the first player was the computer. So maybe you'll keep track of that. And I should note here that in Java and processing, the Boolean data type is actually the full word Boolean, not just bool. All right. So we've got that out of the way, and somehow everything that we do afterwards, it's not that big a deal, right? You're going to start this alternating pattern, right, of human move, computer move, human move, computer move, or vice versa, computer move, human move, computer move, human move. And that alternating pattern, the first step of that will be determined by the value of this Boolean variable, and then after that, the game is exactly the same. So let's get into the nuts and bolts now of gameplay. And not gameplay so much from the tic-tac-toe player's perspective, but from the programmer's perspective. So what are some things that have to happen? I've already done the first thing. I need to draw the grid. So I've got the grid. Now what? So let's assume, just for simplicity, that human is first. So let's assume that the first player is the human. Then, yeah, I have to come up with some way of letting the human select a move. So what are some of the sub-processes that have to happen in a human selecting a move? And Evan started out, right? You've got to register a click. So a mouse click picks a location on the grid. Okay, so we get the location from the mouse click somehow, and we'll talk about that. What happens once you have that location in hand? What are you going to do? Okay, let's lump that all together. Okay. What if there's an O already there? Yeah, beep. So you want to check and see if it's a legal move. Legal move? If not, then what are you going to do with that mouse click? I'm just going to ignore it. So I click on an X, I ignore it. I click on an O, I ignore it. Right? It has to be empty. So legal move? If no, then ignore. If yes, then what? Yeah, so we'll draw an X. Let's assume that this is that the human. Well, we're assuming that the human went first, so we'll draw an X. Okay, so we can do that before or after or at the same time. We draw an X. What else should we do to keep track of gameplay?
There's an X in that location.
Absolutely. So we need to record the move. What's the most efficient way to record moves in this game, do you think? 2D array of 3x3, right? So we'll record the move in a 3x3 integer array. I would say each cell can have how many states? 3 states, right? Empty, X, O. So 0 for empty, 1 for X, 2 for O, -1 for O, I don't care. Just be consistent. So we'll record the move in a 3x3 integer array.
Processing doesn't have a preprocessor. define.
No. No.
Just use constants.
Yeah.
Yeah.
Processing is not a development language. It's not something that people would use to write, professional code or commercial code, right? So it doesn't have some of the niceties of a C++ or a Java or something like that. Okay, so to record the move, okay, what next?
Check the game state, see whether the game is over or not, and then if it's not, then ask the turn to the next part.
So we'll check the game state, and by that we want to know if it's a win or a draw. There's no way that it could be a loss. There's no way that your move could cause you to lose, at least not directly. So we really just need to check the game state for a win or a draw. If it's a win or a draw, what are you going to do? Stop the game, report. If yes, then report. If no, are we ready for the computer move? Yeah, okay, so let's talk about the computer move.
What would the report look like? Another window? Or
It's up to you. Yeah, totally up to you.
Oh, yeah. Like a red thing with cross.
Probably just like an overlay. Yeah, whatever you want to do. You can wipe the whole screen out and just put up you win or computer wins or something like that. Okay, the computer selects a move. How's this going to go?
They will take it if they see it's going to take that, otherwise randomly.
So that's going to be some sort of analysis of the game board. And we can just tuck that all into a function. Yeah? Yeah, so generate move or something like that. So we'll just put this all into a function, generate move. What's going to happen in generate move? It's going to analyze the recorded moves and pick a move based on my description in the assignment. If all goes well, the only change that you'll have to make to your program next week is to this function, generate move. Except it'll be much more complicated. This generate move is going to be tedious, but not particularly complicated. It's going to be tedious because I haven't really thought long and hard about this, but I don't think there are any real clean formulas to detect, XX in various locations on the board. I think you're pretty much just going to have to analyze the board completely. So look at the first row. If there are two X's in there, I need to think about what I'm going to do there. So it is fairly easy to count X's and to rule some things out, right? If there are two X's in there and no open slot, I don't have to do anything, right? So, and there, you check the horizontal rows, the vertical rows, and the 2 diagonal rows. So at most there's 1, 2, 3, 4, 5, 6, 7, 8 different rows that you have to check. But within those rows there are also cases. You can have XX blank or X blank X or 0 or blank XX, and you can have those with O's in place, right? But what we really care, and then, yeah, so it's going to be tedious. Yeah.
So then are we also going to have to, is the way we were talking about our states, we're empty X or O, so we're going to have to adjust how we respond to X's or O's depending on the Boolean.
Exactly, yes, exactly.
Could we also represent 0, 1, and 2 as empty computer and human, and then use the Boolean to interpret which one would print?
Sure. I'm not tying you down as to how you represent the game state. So this will be tedious, but manageable. Generate move, and then the next thing would just be to render the move. And then render the move. Once you render the move, you could probably reuse this. So maybe reuse check game state. And then win, draw. Report, no. Human move. Anything else? I guess kind of separately we could have the report screen.
Is there a way to store like local variables with like cookies or something using processing
To what end?
to have like persistent scores?
I think for one continuous play, you could certainly do that.
Like you get a source of it.
Not, I mean, there are things that you can do, but I'm not asking. I'm not asking.
The world leaderboard, sort of like country.
Okay. Any questions about this overall structure? Then let's continue to talk about some of the options for implementation. So last time we made it this far, where we'd drawn a grid. And that was really just me talking you through some of the basics. What I'd like to talk about next is let's detect the human move. And that's going to require some interaction with the mouse, and that's what I'm going to talk about for at least the next 10 minutes or so. So there are a couple of built-in features with processing. We've looked at built-in functions set up and draw. There's a built-in function called mouse clicked. And whether you have an explicit mouse clicked function or not, the mouse is being watched by processing while the sketch is running. And by default, if you click on the sketch somewhere, nothing will happen. If you would like something to happen, then you explicitly put this function in your sketch, and in between the curly braces, you tell it what you want to happen when a mouse clicks. Let me show you just really simply. Let's draw an ellipse. of a particular size at the mouse location. Don't know why that's not highlighted, but whatever. Mouse X, mouse Y. And hold on for a second. Let's do 10. So there's I have a feeling this won't last very long either. Well, let's try it. It's going to get redrawn. So you can see it appear there and then it gets redrawn. How do we make this persistent? So what's happening there? I'm seeing it very briefly, but then the draw function's happening and clearing it out. So how do I make this ellipse persistent? What I need to do is set. I guess there are a lot of different ways to do this. One thing I could do is just sort of drag this up in here, but then I'm going to get more than I want. Actually, I don't get more than I want because I'm redrawing. But it won't stay where it is. So how do I make it, stay where it is? Okay, well, let's use a couple of variables. So we'll get a couple of variables, say ellipse x and ellipse y. Actually, I don't think it has a. It might have a built-in point. Do you know, Evan, if it has a built-in point? Yeah, there's p vector, which is a bit of overkill. But for now, let's just. Sorry, go ahead.
When I tried to define a point class, it's a reserved key.
Okay.
So I think it already exists.
Okay. So we have ellipse x and ellipse y, which we're going to use to represent the center of the ellipse. And let's just change this to ellipse x and ellipse y, like that. And maybe up here we can set the default value of ellipse x to 0 and ellipse y to 0. Bless you. And with all of this in place, mouse clicked can do the following. Yep. So mouse clicked now is not responsible for drawing the ellipse. It's simply responsible for updating the information associated with drawing the ellipse that happens in draw. This should let us place circles on the screen. Now think about what's happening there. I click and the mouse clicked function happens. And what does the mouse clicked function do? It changes the center of the ellipse, which is being repeatedly drawn by the draw function. And so the draw function doesn't really know that the mouse was clicked. It just draws the same thing over and over again. And it's the variables inside that draw command that are changed by the mouse function, by the mouse click. That's a fairly standard approach. These variables that are used in multiple functions, right? The ellipse x and ellipse y variables are used in setup, draw, and clicked. They should be declared global. In other words, outside of all of the functions, so that their scope penetrates into every function. Questions about that? Now, we don't really want to draw an ellipse. What do we want to do? We want to draw an X or an O in a particular cell. So what we should do is instead let's get some variables to keep track of, at least temporarily, a move. So move x and move y, and let's just set them to something nonsensical to begin with. And what we would like to do is, when these guys are clicked, get the coordinates of the click. In fact, maybe I'll change this to int. Yes, I'm going to change this to int. Think about the grid and think about the coordinates of a cell. What should they be, roughly speaking? And what range of coordinates?
0 to x equals 3, and then between.
I'm thinking even a little bit narrower than that. I'm thinking that I'm going to use these guys as indices in my state array. So if they're indices in the state array, then move x will be 0, 1, or 2, and move y will be 0, 1, or 2.
Just divide by a third of the
I suppose you could do that. That wasn't the direction that I was going to go, but yeah, you could definitely do that. You could come up with a formula: width divided by a third of the width.
or
Yeah.
where you click it.
That's what I mean, yeah, sorry. Where you click divided by a third of the width. Yeah, we could try that. Let's try that. I was just going to go, if you were if you're between 0 and a third, then make it 0. If you're between 1/3 and 2/3, make it 1, and otherwise make it 2. But yeah, you might be able to sort of make that a little bit slicker.
So, should we like create a space object and tuck it into the space object, so just a function that does this depending on the array? This is this.
Let's keep it simple. Okay, so we have move x, and let's try Evan's suggestion. So we would take the current location, mouse x, and divide it by a third of the width. Let's see what that does. And probably we should cast this to an int when we're done.
Mouse x is float.
It's an int. I don't remember what canvas is, so it probably will all work out. Let's see if we don't need the cast. One of the things you're going to find about processing is it's a little more type sensitive than C++. There's less automatic type conversion. Oh, I'm in Vim. Lovely Vim, thank you. I thought I was in processing. Okay, and how can we confirm that this is actually doing what we want? There's some really nice debugging. You can just print to the screen. So let's do that. So we'll print move x. Yeah. So print line will print a string to the screen followed by an end line in C++ speak. So what you have to do is build it a string to print out. And this is fairly typical string building notation. You have the variable move x, which Java or processing will automatically convert to a string. The addition sign really just adds strings together. So if you have string A and string B and you add them together, you get essentially a concatenation of those two strings. So you can use these plus signs to just build strings up from smaller pieces. Let's see if this actually works. 0, 0, 1, 0, 2, 0, 2, 1, 1, 1, 0, 1. Looks like it's all good. Did that not work? Yeah, that worked. Okay, just didn't pick up my click. What do you notice a little bit annoying about this? Here, let me click on this one. In nearly every math class that you take, that should be 2, 1. Not 1, 2. Right? Okay. This is a problem with graphics and arrays mostly in C and Java. C and Java are, let me make sure I get this right, use row major arrays. In other words, the first index tells you what row of the array, and the second index tells you what column of the array. The graphics, on the other hand, are exactly the opposite. The first index, the x-coordinate, puts you in the column of the screen, and the y-coordinate puts you in the row of the screen. So it's not perfectly faithful to think of the screen as just a big two-dimensional array, because it's a column major array instead of a row major array. No end of annoyance. Yes?
Can't you just change how you interpret a two-dimensional array?
Absolutely. But the default, which is what we just did here, we kind of just followed our noses, right? And we labeled row 0, row 1, row 2. It got us swapped around. Absolutely. Now that you know this, just deal with it. Okay? But there's not a natural correspondence between these internal two-dimensional arrays and the screen array. Internal arrays are row major storage. External arrays are column major. The screen is column major. Fortran, column major. So different languages do different things. That's fine. We know that 0, 0 corresponds to this slot. We know that 0, 1 corresponds to this slot. Everybody okay? Okay, let's keep going then. Now what we'd like to do is draw an X. So this appears to be working fairly well, so let's keep it. Much better than what I was going to do with a bunch of if statements. What I'd like to do is, and let's just keep it simple here, I'll try to draw an X, say. And let's draw the X at yeah, let's do the drawing. I was going to say we could update the array. Let's do the array because it'll talk a little bit about how weird declaring arrays are in processing. Okay, so let's declare the game array. So, I may have mentioned this on Monday, I don't remember, but processing and its associated language Java separates the steps of declaring and allocating an array. So in C++, if I want a 3x3 array, I do int state 33. And I get myself a 3x3 array. In Java, those steps, the declaration of the name or the symbol state is separate from the allocation of the memory. So again, etiquette suggests that we declare our symbols up here, our variables up here, and that we allocate the data, the memory for those guys down here. So we'll say state equals new int 3 3. Two-step process. I could, and you do often see this, I could have done this all at once, and that would have been the same effect. But again, the way that I want you to try to follow the guidelines or the basic approach to processing, which is to initialize your variables in the setup function. So here's our state array. And let's think a little bit about this now. To remind ourselves what's happening. Oh, I've gotten rid of my my output command. Wish I could get it back, but yeah. Thank you. All right, when I click on this guy, I get 1, 0. You have to make a decision what you want to do there. I would actually prefer to, in the state array, make 0, 1, X, say. So that's what I'll do. So after that click, down in here, you could say something like if human, or sorry, if first, then state move y, move x equals 1, else something like that. And this will keep track of the moves in the game for you. There's a lot more to it, right? I'm simply overwriting whatever happened to be in the array prior to that. So you would have to be much more careful compared to what I'm doing here. You would have to look at the board and see if it was a legal move before you went and did this. So let's say that I want to render the board or draw moves or something like that. So what's going to happen in draw moves?
Just going to go through the state array and check.
Exactly. So we'll go through the state array. So for int I equals 0, I less than 3, I plus plus. And we'll have 3 cases. If state ij equals 0, then we'll do that. We'll do nothing, say. And here we do nothing. Here we'll draw an X. Here we'll draw a Y. An O, excuse me. I don't know. You can use any symbols you want.
Really?
Just right at the
Exactly. Let's draw an X. So we'll draw an X at ij. Okay, let's talk about the draw function a little bit, and I want to, in the time remaining, talk about a really interesting feature of processing, in fact, any graphical programming language, and that is the transform matrix. So I have to think really carefully about what I'm doing here. I'm going to draw an X in the ij slot. It's kind of hard to come up with formulas, right? What we'd like to do is just have like a diagonal line with slope 1 and a crossing diagonal line of slope -1. And let's have them, and what we want to do is we'll put the center of that crossing at the center of one of the cells. But doing that calculation is somewhat annoying. So make it easy on yourself. Just draw a cross that's centered at the origin, and then use a transform to shift your canvas to the location that you want your X to appear. Draw the X, and then go back. So that's what I'm going to do here. So let's draw an X that crosses, that's of the right size, that crosses at the origin. So that's just going to be 2 lines. So we can make the stroke, say, red. And we want 2 lines that cross, and they're of the right length. We don't have to think about length. Let's go back to, let's go and remind ourselves what this thing looks like. Oh, line 61. Thank you. Oh yeah, I didn't close those guys, did I? Good point. I think that matches draw X.
There's another one lower.
Here? Oh, is there? Okay, got it. Thank you.
You didn't declare it first.
Good point. Where is first anyway? There it is. Yep. We good now? Okay. So nothing's going on really at the moment. Let's imagine that you have an X that's centered right here, and it's sort of got the negative slope line here and the positive slope line here. Or you could even imagine that it's here. How far? Well, let's think about it here. So where is the upper left-hand corner of the X in terms of the size of the canvas? So
Negative X canvas over 6.
6, yeah. Is that what you said, Ben? Anyway, so yeah, negative canvas X over 6 in the X direction, and then negative canvas X over 6 in the Y direction gets me at that corner. So let's do that. Line negative, I think I called it canvas X. So that's the negatively sloped one. What's the positively sloped one going to look like?
trade x coordinates. We trade out the negative.
So I can go positive x, negative y, and then negative x, positive y. Is that going to do it for me? And just to test this guy out, I'm going to go up here and do draw. I'll just put my draw x right here. And if we've done this correctly, we should see not much. We'll see one little red piece sticking into the upper left-hand corner, and the other three are off the canvas. Okay, and we should also reset our stroke every time. But yeah, the X is mostly out of the picture, but the center of the X is right there. Okay, almost done. Let's reset the canvas here, the stroke to black. So now the stroke is black, and then it goes in here and turns red, and then it comes back up here and turns black, and so forth. So that should fix the color problem.
So the lines are twice as long as they need to be because the negative ones and the positive ones are set. Right. But
So now let's talk about how you can take advantage of transforms to draw this thing. There's three kinds of transformations that you can do in processing. There's translation, which essentially takes the origin and moves it somewhere else. There's rotation, which takes the canvas and rotates it through an angle about the origin. And there's scaling, which will take an object and either shrink it by a factor or blow it up by a factor. And you can layer these things. You can have, you can do a translation and a rotation and a scaling to accomplish a particular effect. The problem is when you start layering these things on top of each other, they get really complicated. And like stroke color or fill color, when you issue a translation or a rotation or something, that stays in effect until you undo it. So to reduce that complication, there's a stack of translations or isometries on the canvas. And what you can do is take the current collection of isometries and push it onto a stack and get a fresh one, do stuff to it, and then throw it away. That's what I'm going to do here. I'm going to push a new set of isometries onto the canvas. I'm going to do a bunch of stuff. In particular, let's translate the origin. And we'll translate the origin to the center of the first cell. So that's canvas x over 6, canvas y over 6. Then we'll draw the x, and then we'll pop the matrix.
Wait, why are you translating x over 6? Don't we want some isometries in there somewhere?
Not yet. I'm just going to try to put it in the first cell,
Oh.
the upper left cell. And then we'll generalize. So what's going on here is the translate command takes the origin and moves it to the center of the first cell. And then I know how to draw a line that an X that crosses at the origin. And now, instead of messing around with formulas for how to draw X's at every different cell, all I have to do is translate the origin to the center of each cell. Let me get rid of that guy. I also don't like the fact that you can that the X is hitting the edges. And so let's scale it a little bit. Shrink it down a little bit. And That's an excellent question. I don't know. We could really shrink it down and see what happens.
I think it does because it's all drawing in like vector graphics right now.
So let's make it really small. Certainly.
Yes.
That's a yes. But the nice thing is, you can draw these simple objects. You can create simple objects and then put them wherever you want at whatever size you want. And you can even rotate. Let's go back to 9 here and let's just do a quick rotate. I think it's radians.
You have to do all this stuff before you draw.
Yes. I can't remember if radians is what it's called. I'm not sure. Oh, I didn't write. Okay. Duh. Okay, so why did that get so big?
Well, it's because we took a diagonal, which is...
Oh, yeah. Got it. It all makes sense. Thank you. So there's a lot that you can do with translate, scale, and rotate. I'm kind of out of time, but essentially what you would do now is just use I and J to translate to the center of whatever cell you'd like to draw in, and then draw. And you push the set of isometries. You push a new layer onto the set of isometries. You do whatever you need to do, and then you pop it, and they're gone, and you don't have to worry about them anymore. We'll talk a little bit more about this next time, finish this off, and then we'll start maybe talking about game theory and game trees. I'm done.